Hello and welcome to the sixth of our 8-week webinar series titled Advancing in Predictive with Alteryx. Here's, just before we get started, an overview of our upcoming webinars. So today we'll be covering decision trees, and next week we will be covering crosstab and transpose. We'll take a week off for Tableau conference and come back on November 21st to finish off with time series. And all of these webinars will be on Thursdays at 12 p.m. And a few notes before we get started. Yes, this webinar is being recorded and the link will be available before the end of the week. And we will have a Q&A session at the end of this webinar, but you are more than welcome to enter your questions into the Q&A panel as we go along. There are a few files that we will have available, and I'll share the link in the chat box of this webinar. And a few introductions. My name is Rachel Mason. I'm the marketing specialist here at Teknion Data Solutions, helping out with this series, and Teknion is happy to be hosting this series. Covering today's webinar is Dr. J. Kyle Roberts, who is a data scientist here at Teknion. A little bit about Kyle: he's held professor positions at Southern Methodist University, Baylor College of Medicine, and the University of North Texas. He's also co-authored the Y-HAT package in R, and he's an expert in multi-level modeling and co-authored the Handbook of Advanced Multi-Level Analysis. So without further ado, I'm going to hand it over to Kyle.
All right, thanks, Rachel. So glad that all of you are on the call again, and we are. We wanted to let you know that as Rachel's going to be putting in the chat box right now, the link to where you can go to grab the files for the webinar. And so this will actually be especially important today because we have one file that's actually we have pre-built for you, and because there's a lot of stuff that we're going to be talking about on data preparation in order to look at decision tree. And so as we add those, it would probably make sense to go ahead and download those files. There's a data set there, and then there's or actually a couple of data sets, and then there's one actually workflow. The second thing is, and we've been advertising this every week, is that we do have predictive macros on our website at this at the bottom link there, and that's going to take you to this page. And so we have two macros up currently, and we will be adding more. One is the K-means cluster selection tool that we have developed, and then the other one is the Y-HAT tool. And so if you watch the previous webinars, we talk about these extensively. You're welcome to download them for free. And so it actually is an installer that will install a tab on Alteryx and actually put both of these macros inside there. We give them away for free, but we just want to know who's downloading them. And so we'd encourage you, excuse me, we'd encourage you to do that. So today, when we're talking about decision tree, we're kind of into a different area. So we're going to start to talk about classification. And whereas before, when we were thinking of linear regression or even logistic regression, we're actually predicting an outcome in linear regression that outcome is in a linear scale, or even in a dichotomous scale in the case of logistic. Or so we would think of that as being an intervally or ratioed variable, such as like some score on some test or something like that we're trying to predict, or how many examples of something exist when we're looking at observations or something along those lines. So today we're actually going to look at something else, so like classification, meaning that let's suppose we want to predict if someone is in group A, group B, or group C. Now, those of you that are classical statisticians, when you're thinking about this, you're probably thinking not decision tree. You probably think in terms of something called discriminant analysis, or even predictive discriminant analysis. And so if that's you and you're thinking about this right now and going, okay, well, if we're predicting what group you're in, that's just discriminant. It's going to be a little bit different than that. And so, but that is kind of a nuance of what we're doing today. We're just going to do it a little bit differently. And we're going to weight our variables a little bit. So if you are thinking in that term, that's okay. We're going to talk about a little bit different terms in decision trees. So let's talk about kind of how a decision tree works. So let's suppose our outcome variable is we want to know how fast people are driving. So let's say we have a data set where you have 10,000 observations, and how fast we want to know how fast people are driving in each of those. And all we measured was like weather conditions, and And so we have two things that we measure in weather conditions. The first one is it snowing, and then the second one is it raining? And then we ask people, okay, how fast are you going right now when they're in their car? And all we're looking at outside is it snowing, is it raining? Okay, so what the decision tree will do is it will treat that miles, how fast someone is going. It will treat that as the outcome variable. And so what we may start with, and in that case, that's a regression-based decision tree, because our outcome is actually not a group, it's a continuous variable, but we can also do it for groups. And so I'm just going to illustrate it with a continuous variable, and then when we do the actual data set, I'll illustrate it with a group as an outcome variable. So the first question is it snowing? And when we run all our data through, and so the decision tree will come back and we'll say, all right, this is the most important factor first. And what the decision tree will break it into two groups, and it will say, okay, if it is snowing outside, yes, then most of the cars, we're going to classify them in what we're going to call our 30 miles per hour grouping. And so that's the first branch of this decision tree, is that it's saying, all right, if it is snowing, then we're going to put a group together of cars that are going 30 miles per hour. And then if it's not snowing, we're actually not going to say how fast they're going to go. We're going to actually ask another question, so a follow-up question on that. And that question would be, is it raining? And so if it's not snowing, but it is raining, then we would classify that group as going roughly 50 miles an hour. But then if all these are on highway, then if it's not snowing and it's not raining, then we're going to group that, or we're going to classify that group as being like our 75 mile per hour cars or 75 mile per hour travelers. Okay, so the reason that we call this a decision tree is, as you can see, it's what we're doing is we're taking cut points. And for the simplicity of today, we're just going to look at a dichotomous cut, meaning we're just going to be able to say a yes or no, or it's above a value or below a value. And so that there are only two options to each question. So in this case, is it snowing? And then also as a follow-up, is it raining? Now, for the terminology on this first question that we ask, meaning the first one that the decision tree says, all right, this is the most important one, we call that the root node. And the reason we call that the root is because in the process of letting our software create a decision tree, this is the first and most important question, meaning that we get the best classification by starting with this variable or this question. Or another way of thinking about this is that we get it's the one that explains the most about our data. And so we generally start with that one, and then we start working down to saying, all right, after we know whether or not it's snowing, we need to know in our follow-up an internal node of, okay, what's a good second question task? Now, again, a lot of this is mathematical, but the point of it is that you're creating a decision tree that is based on hierarchy of importance of questions to ask or importance of variables to be able to put in there. And then these last parts, we call these leaf nodes. So that's actually the output that we're producing. And so that would be the node we'd be thinking of, is that we have three nodes that we end up with: a 30 mile per hour group, a 50 mile per hour group, and a 75 mile per hour group. Okay. Now, again, this is a really high level way of thinking about this. And so there's not a ton that we would necessarily want to pull more out of this, other than just to talk about this is the structure of how decision tree works. And so what we're going to do now is we're going to fire up Alteryx, and we're going to work through two examples. The first one being a rather simple example, and then the second one being a much more complicated. Now, if you were in our K-means course, then you'll probably recognize this first data set. This is called the MT Cars data set. And again, it's up on our website. And if you want to download it, you can pull it in now. But this data set, I tell you what, we'll go ahead and run it just so we can actually see what it is. And so, hold on, I'm having trouble with Alteryx wanting to come up. But if you'll recall, from those of you that were in this session, there we go. Not sure why my computer did that, but hopefully it's better now. So the first one, we're looking at this MT Cars data set. We have a whole bunch of information on cars, on like how fast their miles per gallon they get, and how fast or how big their engines are, and how many cylinders the engine has. And so as we're looking at this data set, we see that there's miles per gallon, there's cylinders, there's cubic inches, horsepower. weight pounds, time 0 to 60, the year it was made, and then the brand. And so what we want to do is let's say we want to predict or try to classify by the number of cylinders. So we would typically think of that as a nominal coding. And so that's a grouping outcome or a classification outcome. So I'm going to I tell you what, let me move this a little bit over just so we get out of the way there. There we go. Okay, so what I'm going to do is click on this decision tree, and I'm going to select as my target variable the number of cylinders. And then I'm going to have as predictors of that, the miles per gallon, the cubic inches, horsepower, weight, all of that stuff. Okay, we're going to actually predict that. And then I'm going to click on this customize button because there's a couple things I want to see on here. And the first is that it's probably going to come up as model. We're going to choose the algorithm R part. That's fine. That's generally the one I want to, because it's going to give me some output that actually is really interpretable for me. And then I want to click on the plots, and usually I can turn off the prune plot, but I am going to pull the tree plot and make sure that's on, okay, so that I can see what the tree is going to look like afterwards, okay. We'll go ahead and run this, and again, it will take just a second to run, and once it does, we'll start to see here are our outputs. And so I'm going to start with this bottom one, just because it, I think, gives us a really good picture of kind of what's going on with our data. So as you can see on this, the accuracy we have at 95.8, meaning that how good a job this decision tree is doing at classifying each person, or I mean each car, into the number of cylinders, is that we're getting almost 100% correct, meaning this decision tree is doing really, really a great job, okay? We'll come up and we'll look at then the report, and at the bottom of the report, this is really where I want to spend most of my time, okay? So this first node is the root node, okay? And that root node set up for us a dichotomous question. And what it did is it said, okay, that variable that you had that's cubic inches, meaning how many cubic inches is the size of your engine. The decision tree algorithm came up with the first question of saying, is it below 160 cubic inches or is it above 160 cubic inches? And so it says, yeah, if it is below that amount, then we are going to call that group the 4-cylinder group, because remember, that's one of our possible outcomes. If it's not less than 160, then we're going to have another node, okay? So this is an internal node that's the same, is another question, but again, notice that it's up based on the same variable. So even though we asked the root node here a question about cubic inches, we're actually going to further parse that variable out in cubic inches and say, okay, now is it smaller than 259 cubic inches? And if it is, then we're going to say that's a 6-cylinder. And if it's not, then we're going to say that's an 8-cylinder. Now, the great part about this tree plot is that it gives you a lot of information about how many correct classifications we are making. So if you see in here, there is 76 out of 77 are correctly classified as having 8 cylinders. When in fact there's one that doesn't fit that. And then also the same with the 6-cylinder group, there's one that doesn't fit that. And then it looks like there are 7 in the 4-cylinder group that don't fit that. Now the reason that is because we have a couple of cars that have 3 cylinders and a couple of cars that have 5 cylinders, and that's kind of where those misclassifications are happening, okay? So this gives you a really good idea of how your tree is working. Now, you may be asking yourself the question, hey, Kyle, but didn't we include a whole bunch of variables in our model? And you're right. We included miles per gallon, cubic inches, horsepower, weight, time to 60, year, brand. But in our output, we found that the only variable that actually looked in there or appears in there is the cubic inches. Okay, now why is that? Because when the algorithm is running for a decision tree, it only includes variables or decision cut points that actually add information to your model or make your model better. And so what in essence this one is saying is that, look, your car or your model is doing so good at predicting the number of cylinders with just this variable, cubic inches, that we don't even need the other ones. They don't add anything extra to the model. So it's a good way of kind of determining parsimony, especially when you have, let's say, 700 variables that you want to include in a model to try to predict some sort of grouping cluster or some sort of classification, that now you can enter all those variables in, and even though it may take a long time to actually run, in the output of that, we can actually see, all right, only the variables that matter and only the cut points that matter will be included in our analysis. Now, again, how we're able to determine that is a little bit beyond the scope of today. We probably need a good solid 4 or 5 hours to really talk about decision trees. But regardless, here's what's going on. Okay, so it's just saying, all right, only the cubic inches is the one that's actually adding something to our analysis. And so we would just go, okay, all these other variables we don't need. And in fact, we can even test this just to make sure, is that we will rerun this without those other variables, and we'll say, all right, let's run it with just cubic inches in there. And my computer's wanting to freeze up again. Okay, there we go. So we'll run it without all those others in there, and we'll see what our output looks like then, and we'll compare it to what we just saw. Okay, so our results are ready. I'll render that down, and sure enough, less than 160 is our first one, and then less than 259 is our second, our internal node, okay, that appears on there. So we're getting exactly the same results with just one variable. So now, this is a good way also too to help you when you're trying to find out, all right, what are the variables that matter to me in determining, in this case, how many cylinders a car has, or in determining some sort of clustering routine. Okay, so that's it in a really short nutshell. So let's get a little bit more difficult, and let's start to look at, this is the workflow that I actually put available on the website. So here's what we're going to do with this data set. So let's suppose I've got some, and this is also too, it's we're going to be doing some of the things that we were talking, that Dina Sanchez talked about previously, about using some joins and trying to, parse out our data a little bit. So what we're first looking at is this great data set that we totally simulated. This is not actual data, but we simulated it for our own purposes, that has hospital readmits as being the outcome variable. I mean, we're going to try to predict that. And so we're going to think of this as a classification model, because it's were you readmitted or were you not readmitted? And so we have all of these cases, and then we have, this is the case number, meaning like a person number. And we have, did they have an in-hospital event? We have a knowledge test that we gave them on how much they know about the reason that they're in the hospital, and then also the treatments for what they have. We have the number of previous admissions. We have the number of comorbidities, meaning what other things do they have present in them, such as maybe, let's say, obesity or high blood pressure or high cholesterol or history of heart disease or something like that. So comorbidities, and then we have the date that they were admitted. Now, I'm going to, I tell you what, I'm going to turn off these other containers just so we can look at this first one. Now, the reason I want to do this is because as we start to look at this data set, you will see that one of the problems is that, like, case number 1003 actually appears 5 times in our data set because they've come in on 5 different dates. Okay, so again, the previous admissions is held to 4, the comorbidities is 4, the knowledge test, and then whether or not they are readmitted is also based on each of those observations. And so what we're wanting to do is we only want to consider the most current time that they're in the hospital. So again, the reason why they're in the hospital right now. And so what we are looking at is, again, here's each unique case and the number of times they appear in our data set. So a lot of them are 5, 4, 6. Some of them only appear 2 times, some appear 1 time in our data set. But what we want to do is we want to grab the most current case. Okay, so what I'm going to do is grab a select tool, just so I can make sure, because this came as a CSV, I need to make sure that everything's the format I need it. I'm going to use a summarize tool, and what we're going to do is we're going to do a group by case, and then I'm going to take the max date, meaning the most current date, and then we're going to join that back into the original data set. And when we join those in there, we'll keep the case from the left, and then we're going to take out that max date and then keep all the information from the right. And what that does is that produces for us a data set in which in this data set, we only have one observation for each person, the most current observation. Okay, that's the most current observation that we have for each person. All right, that's the reason we want to do that is because in a decision tree, you're only going to want, like in a case like this, you're only going to want to predict, in this case, a classification of whether or not they have been readmitted on the current. And so, because we don't care about past readmits for the same person, we only care about the current or most, the one that's just appearing now. So here we're going to set up the decision tree. Well, if it'll let me click on that, there we go. Okay, so here we're going to set up the decision tree, and I'm going to go ahead and I am going to pull in a sampling tool that's going to let me pull out some of the data to actually run in the decision tree, and then I'm going to run a lift chart to compare the decision tree to the forest model. So let me get that off. Okay, so I'm going to run this, and then I'm going to pull out half of the people to actually estimate my model with, and then half of them for the validation for the lift chart that we're going to talk about in just a little bit. So here's how I'm going to set up the decision tree. The outcome variable is whether or not they're readmitted. Again, the case number is not going to be helpful, but the other 4 variables are going to be helpful to me. Then I'm going to run all 4 of those, and then under the customize, remember under the plots, I want to see, I'll tell you what, that prune plot is, sometimes this does this on mine. There we go. So I want to make sure that the tree plot is actually there. Okay, so I'm selecting that, and then we're going to go ahead and we are going to run this model. Okay. That's great. All right. And we're going to run it, and then we'll see the output of this. Now, remember, again, what we're doing is we're trying to classify our people into 1 or 2 groups, the readmits and the non-readmits. And we're seeing if we can get enough information from those other 4 variables to actually help us out on this. So let's start with this middle one. Okay, and our output here. Well, I'll tell you what, let's actually start with the bottom browse so we can get an idea about how good we're doing. Okay, the accuracy on this is about 80.5. That's not bad, right? That's giving us a pretty good level of information. And so about 80% of the people were correctly classifying if we know those 4 things. Now, if a hospital, those of you working in healthcare, if we did actually get this high, 80%, that we would be jumping up and down. That's really, really good for predicting hospital readmits. Okay, so let's look at what that tree looks like. And I tell you what, I'm going to go ahead and blow this up. There we go. And let's look at this tree plot down here at the bottom. Okay, so first thing we want to look at, the root node, is the in-hospital event. And remember, that was coded as 0s and 1s, meaning did they or did they not have an in-hospital event. And so if that's yes, and then no, so if it's less than 0.5, meaning yes. So in other words, if they were a 0, because 0 is less than 0.5, then we would predict them to be a 0, meaning they will not have they're probably not going to be readmitted. Okay, so I know that yes and no is weird, but we really have to look at what the question is. The question here is, did they have an in-hospital event less than 0.5? So that means the 0s are over here because that's the true one. The 1s are over here because that's the false one. Okay, so there's the case first. That's the first. There's our root node, and now we have our other nodes that's going to be asked. The second question is, did they have comorbidities that were greater than or equal to 1.5? Okay, so here's the crazy thing. Did they have an in-hospital event? Yes. Yes, and then there's no. Okay, and now, were the comorbidities greater than 1.5? If it's yes, okay, then we're predicting them to be a 0 because the yes is going to the left. If it's no, then we're predicting them to be a 1. Now, this may be counterintuitive to you. you may be thinking, all right, that if they had a lot of comorbidities, then they should be a greater likelihood of being readmitted. But actually, they're not, because we're looking at them in respect to also whether or not they had this in-hospital event. Okay, and so there seems to be some sort of cut there, that people with a lot of comorbidities, meaning they're greater than 1.5, that's the yes. Okay, and we can even see that up here. Okay, people with comorbidities that are greater than 1.5, we're predicting them to be a 0. But if they're less than 1.5, we're predicting them to be a 1. Okay. All right, so that's what we're looking at there. All right, so this is giving us information. I know it may seem counterintuitive, but it probably has something to do with that in-hospital event is actually explaining so much of what's going on here, that what's just the things that are left over are the only things that are kind of being able to be explained. Okay, so there's 2 variables in there. The first is the root. Did they have an in-hospital event? If the answer is no, which means they're less than 0.5, so that's 0. That's what we're predicting. If they did have an in-hospital event, then the next question we need to ask is, did they have any comorbidities? And if it's greater than 1.5, meaning so greater than or equal to 1.5 or 2 or above, then we're actually predicting them to be a no. But if they're less than, then we're predicting them to be a yes. Okay. All right. So that's what we're seeing so far in this analysis. Now, you may be thinking, all right, well, that's nice, but I don't want to just run that. Oh, come on. Sorry. I don't want to run just that. Maybe I want to also run a forest model. Now, here's what a forest model is. It's like a whole bunch of decision trees run at once. And so I'm going to click on forest model, and we're going to set it up in exactly the same way. Readmit is going to be our outcome variable that we're looking at classifying. Whether or not they had an in-hospital event, knowledge test, previous admissions, comorbidities, and then a number of trees to use. I'm going to cut this down just for the sake of it being able to run really quickly, okay, to 25 trees. And then once we have that, what we can do is run both of these, and then we are going to pull the output from both of those into a lift chart. And what the lift chart is going to do is it's going to tell us, all right, which of these models works best. So I'm going to take the output node from both of them, and I'm going to union those into my lift chart. And then I'm going to take the new data. This is the validation data. I'm going to pull that into the bottom of my lift chart, and then that will give me an output that will let me know, all right, which one is actually performing better. So this is going to take just a second to run, but as it's running, we'll be able to see which of these works better. Now, again, too, a forest model is just a whole bunch of different types of decision trees run against each other. And then the idea is that when you average across all of them, you can get a little bit more information. Usually, always, the forest model is going to be a little bit better, but we lose something in terms of parsimony, meaning it takes a lot longer to run. And usually, we would never do 25. We might do like 50 or 100 or something like that. So the forest model, you can see the output from that. That looks very similar to here are the different numbers of forest models and the error that was run. Remember, we only ran 25, okay? And then also, you can see this is the part that's just pulling the data through. We look at the lift chart results, and this will tell us, all right, which one's doing better, the forest model or the decision tree? And what we want on this chart is that what we want is that in this weighted cumulative response captured, we're looking for charts that actually have a larger curve. In fact, they're less vertical, or I mean, less of a straight line and more of like an outside curve like that. That's what we're looking for. That's usually the best model. But when we look at this, we see that the forest model and the decision tree are not that much different from each other. They're both performing pretty close to the same, okay? And then if you're looking at the decision tree versus the forest model on the percentage and then the gain and the lift and the area of those, so we look at the area under the curve, where the decision tree is 0.60, for the forest is 0.642. That's like an area under the curve. That means we're getting, another way to think about that is you're getting about 4% more performance from the decision tree than you are the forest model. In my opinion, it's probably not worth it, just because how fast the model is going to run when you have big data sets. It's probably might not be worth it. But again, if precision is everything that you're about, then you might want to look at this. The other thing too is, I think, in my opinion, this right here is really easy to explain to someone who has no knowledge of statistics. And whereas when I start trying to explain the output that's coming from the forest model, it is rather hard to look at, other than we see that, look, comorbidities and then hospital events, here's the importance on those. Okay, previous emissions and knowledge tests is not that helpful, but actually that we are seeing that they're weighting comorbidities to be more than the in-hospital events for the forest models, whereas we had them reversed inside the decision tree. But again, not that much difference on those. So that is a really quick overview of what's going on in decision trees and forest models. Again, for me, I stay here for the most part, because in the decision tree world, because I think it's much more palatable to those that I'm trying to explain than trying to explain in this forest model. Much more easy to interpret, easy to understand. Okay. So this is generally the area in which I live, is just this decision tree area, and I usually don't ask too many of the models that I want to run, especially if it's really big data sets. Running a forest model generally takes a very long time. Now, having said that, if we did want to, and we're going to play for this because we have time, we're going to play with this for just a little bit. I'll tell you what, actually, we'll play with the decision tree small one for just a little bit. Let's, in this case, let's see if instead of predicting cylinders, okay, we can predict what we talked about before, the number of miles per gallon, okay? And the reason I want to do this is now we're taking we're taking what was a classification and we're making it a regression, okay? So I'm going to select all of these, but then pull miles per gallon out. And then we are going to run our model based on this. And the reason why is I want you to see the difference between what a outcome for a classification model looks like and an outcome for a decision tree. For a regression base. So this one's going to be different because our outcome variable is actually regression based as opposed to the classification based. And then let me show you what the output looks like on this, and then we'll go to questions. Okay. All right. So when we look at this again, I want to run down to this decision tree. All right. Here's the interesting part. All right. So the very first thing that's asked, the very first question that's asked is the number of cylinders in the decision tree. So here's our root node. Does it have 3, 6, or 8 cylinders? Okay. And if it does yes, then we're going to go to this side. And if it's no, then we're going to go to this side. Okay. So let's suppose we have a 6-cylinder car. Okay. So we're going to go to the yes side. And then we ask the question of how many cubic inches are there? And if it's greater than 284, right, okay, we're going to go over to this side because yes is on the left. If it's greater than 284, we're going to go to yes. Okay, if it's less than, we're going to go to this side. And then what we're going to see next is if the year is less than 1978, okay, so that's our 3, 6, or 8 cylinder with a cubic inches on the engine that is bigger than 284, and it was before 1978. We're predicting that we're going to call that group our 14 mile per hour group. 14 miles per gallon group. Okay, so each of these variables down here, these are the groupings for our outcome variable, which is miles per gallon. So we're going to call this one a 14. We're going to call this one an 18, meaning that it's still a big engine. It's a 3, 6, or 8 cylinder. It's still a big engine, but it is greater than 1978. So we're going to gain about 4 miles per gallon. But the reason that I think that this is important to do is that as we're looking at this, we can actually get a lot of information that we can explain very easily about what do the top mile per gallon cars look like, okay? And so the top mile per gallon cars are either, so remember our possibilities for cylinders were 3, 4, 5, 6, and 8. So either it's a 4 or a 5 cylinder, okay? Right, that's this way. The horsepower is So we're looking at this one. So that means the horsepower is less than 76 horsepower. Okay. And it is newer than 1978 because that, yes, less than is this way, but newer is this way. Okay. And the horsepower is less than 66 horsepower. Okay. So it's either a 4 or 5 cylinder car that's newer than 1978 and the horsepower is somewhere between 66 and 77 horsepower. Okay. That's the most efficient car that we have in our data set. Okay, so do you see how now this picture is worth 1,000 words to me? That I can take my data set and go, okay, we can classify this miles per gallon into these chunks based on what we want to know or what we're wanting to represent from the data. So now we get a good way of understanding, hey, the 23 mile per gallon group, what they look like is either a 4 or 5 cylinder, that its horsepower is greater than 76. It was built before 1980. And the cubic inches are greater than 108. Okay, that's my 23 group, right? Now, again, it's not perfect, but it does give you a lot of information to be able to now, if you're doing stuff for your work or you're doing stuff for your customer, this is a great picture to be able to take back to them and go, hey, I understand the groupings of the miles per gallon and what makes those different types of cars, okay? All right, that was a lot. So hopefully you have the ability to go back and be able to look through that. And so I know that was a lot to drink from, almost like drinking from a fire hose, but hopefully we got plenty of information for you. I'm looking through the questions and I don't see that we have any questions. And so I tell you what, I will turn it back over to Rachel, but I will say this, that feel free to look on the Teknion website. And if you do have any questions that you would like to send over to me, I'd be more than happy to help them, to answer them. My email is there on the site. And then also feel free to use these data sets. Again, it's all heuristic data. It's not real data. So use it as often as you would like. All right. Rachel?
Great. Thanks, Kyle. So next week we will be covering crosstab and transpose. So if you are interested, Dina Sanchez will be covering this webinar. Go ahead and register for that. And this webinar was recorded and the link will be shared before the end of the week and posted on the website along with the data file links and the macro links. Thanks so much for joining us today.
Yes, thanks everyone.